Okay, good. That's the way that I want, the way that I like. We start with the syllabus all over again. Here is the syllabus. And by the way, you should be able to see your grade there, right, in Canvas. There was a little problem there in Canvas. I managed to resolve it, and now you have your grades in the way it's supposed to be displayed. Today is November 19th, 2025. We started talking about linear momentum, and we will continue talking about linear momentum. Labs 2 and 3 are due today. Labs 2 and 3 reports due. Labs 2 and 3 reports due, right? Let's put it this way. So let me see. We are going to have our third exam. Third exam. This thing here. You go. Third exam in 2 weeks. 2 weeks. Yeah, 2 weeks. We are covering chapter 7. So today we're going to do lab 4 as well. Let's see if we can finish linear momentum, right? If we can finish linear momentum, then next time we start talking about chapter 8. One more student here to come. Where did we stop? Here you go. Right in here. We look at two different types of collisions: inelastic collision and explosion, what I call explosion. Not every book uses the same words that I use to describe it, right? In the reverse of an inelastic collision, mechanical energy is not conserved, is not conserved. Okay, totally elastic collision. In this case, mechanical energy is conserved. Okay, in this case here, is not conserved and decreases. Okay, let's put it this way. In inelastic collision, the final mechanical energy is less than the initial mechanical energy. But in the case of explosion, mechanical energy increases, is not conserved and increases. The final mechanical energy is greater than the initial mechanical energy. Mechanical energy here is conserved, which means the initial mechanical energy is equal to final mechanical energy. And then we have the partially elastic collision, in which mechanical energy is not conserved either. And what happens? It's not conserved and it decreases. Okay. Those are the 4 types of collisions, right? Between quotes, because explosion is not a collision. The explosion is the reverse of a collision, but I should characterize it as being a collision. Insert page break. Today is 11/9/25. And we finish Wednesday. Totally elastic collision. That's what you're going to cover today. Oh. Okay, I'm trying to get something here, and so you can continue. Let's see. What? That's so odd. Oh, yeah, okay. I got the wrong document here that I cannot get it. Okay, now I should be able to get what I want. Okay. Okay, so totally elastic collision. By definition, a totally elastic collision is a collision where the mechanical energy of the system is conserved. Okay? In the first two cases we studied, mechanical energy is not conserved. In the first case, which was the simplest one that you're going to see, in elastic collision, the mechanical energy decreases. In the second case, which is an explosion, mechanical energy increases. And in this case, and because of energy here in this case is conserved, the problem becomes more difficult. Okay, well, let's write that down. The simplest collision problem you will see is the 1D inelastic collision, because it involves a single equation. Mathematically speaking, it's easier to solve because it has just one equation for you to solve. Okay, when we start talking about explosions and totally elastic collision, then the problem starts to become more and more difficult mathematically. Okay, uh, in the case of explosions and totally elastic collision, comma 1D, and let's put 1D explosion in the case of 1D explosion, right? And totally elastic collision, comma, you will have at least two equations that need to be solved, making this problem more challenging in mathematical terms. Okay? So let me give you a real life example of a elastic collision, a totally elastic collision. The ball's in a pool table. Whoever has played pool, those balls that we play with, they undergo a totally elastic collision, an almost totally elastic collision. Okay, the ball bounces out of the other, right? When they collide, it bounces out of the other. They don't stick to each other like we have in an inelastic collision. And let's not forget, we're still talking about 1D because it's the simplest problem, right? When we start talking about 2D collisions, then the number of equations start increasing. Okay, so higher difficulty. And now, we're going to do an example of elastic collision. Two objects having the same mass undergo a totally elastic collision. After collision, after the object one collides, right? After the object one, after the collision, yeah, okay, after the collision, comma, object one bounces off object two. Yeah, but let me put bounces off like that, you know? It's not as exactly bounces off, but it doesn't stick to each other. Object number one has an initial velocity, v01, undergo a 1D, okay? Let me emphasize here, 1D totally elastic collision. And you can reproduce this type of collision in real life. I'm gonna show you here my play the movie, right? I love to play the movie here in my classes. Here you go. I'm playing pool. The masses of the objects are the same. Here's one of the balls, here's the other one. It is approaching, the first ball is approaching the second one. Let's put another frame here for this movie. Here you go. I'm gonna put another frame right in here. I'm assuming that friction can be neglected. Here you go. The ball approaching, about to collide. When it collides, you gotta see that in your mind, what happens. The force that one applies to two, the force that two applies to one. Because those two objects, is Newton's third law of motion. Because those two objects are interacting with each other, and by interacting, I mean they are applying forces, okay? The force that one applying to two is equal to the force that the two apply on one. The force that two apply on one, equal in magnitude, opposite in direction. Here you go. Equal in magnitude, opposite in direction. And what we see in real life, if you were to do this experiment in the pool table, okay, two masses, and if you were to reproduce this experiment exactly in the one-dimensional, in a single line, right? And it's possible to do that. I have already done that. What happens? The first object comes to a full stop. Hey, wait a minute. No, that's not this one here. Okay, let's see. Here goes. The first object comes to a full stop. The first object comes to a full stop because of this force. F2 in one, that's to the left, right? This force decelerates the first object and bring it to a full stop. And then what we observe, the second object takes off with the same velocity that the initial object had. And we can prove that mathematically using conservation of linear momentum and conservation of energy, conservation of mechanical energy. So let's play here. Let's get this other frame here of my movie. Okay, here you go. This one, let's see. I'm gonna get this one a little bit closer. And now we can play the movie, right? Here you go. Here you go. First ball approaching the second one. They collide with each other. Look at the forces that are that the ball are experiencing. And then I'm going to prove mathematically that the final velocity of the first ball is going to be 0. And the final velocity of the second ball is going to be exactly the same velocity of the other one. Okay? So how do we do that? We do exactly what we have been doing before, but with the additional detail that we have to use conservation of energy in my equations. The problem is a one-dimensional problem. Consequently, this equation, even though it's a vectorial equation, is going to end up being a single scalar equation. Okay, because the object do not change height, right? There is no change in potential energy. There's no change in potential energy. It means the final potential energy is equal to the initial potential energy. And what you end up having is just the conservation of kinetic energy. You go? The initial momentum is going to be the initial momentum of 1 plus the initial momentum of 2. The final momentum is going to be the final momentum of 1 plus the final momentum of 2. Okay? And now you're going to appreciate the fact that this problem is more difficult to solve. You're going to see what happens. We go. Next step, we have to spell out the initial momentum of the two objects. mv01 plus mv02. Here you go. mv final 1 plus mv final 2. And the kinetic energy is going to be the sum of the kinetic energy at the beginning and the sum of the kinetic energy at the end. Okay, because this is a totally elastic collision, right? Totally elastic collision. V final 1 will not be necessarily equal, to V final 2. This is equal only in the case of an inelastic collision. It's not going to be necessarily equal to V final 2. And that's what introduces a difficulty in the problem. In the totally elastic collision, this velocity here is going to be equal to this other velocity here, which makes the problem simpler to solve. But not in the case of a totally elastic collision. And we go like that. V final 1, right? V final 2. And this V final 1 and V final 2 are going to be part of this equation. I hate why the thing keep on showing here. I hate when the thing happens. And I do not know how to get rid of this thing. Maybe I should turn off Copilot. You're right. Let's see. Yeah, it doesn't have. But anyway, I have KE1 plus KE2 here. And I really do not know how to get rid of this annoying thing. Make change, visualize the table to right set default paste. Keep tests only. I don't know. Yeah. Okay. Now I got rid of it. Okay. Looks like I had to release the buffer from whatever. And then we have we're going to apply all the conditions that we already know in our problem. Initial velocity of 2 is 0, so this term becomes 0. Because the initial velocity of 2 is 0, 2, then the initial kinetic energy of 2 becomes 0 as well. Okay, at this point in time, I do not know what's the final 1. I do not know what's the final 2. Okay, so if you're solving this problem for the first time in your life, you would not know the final velocity of 1 and the final velocity of 2. And I'm going to prove that's going to be exactly what you saw there. Okay? 2 equations, 2 unknowns, and 2 equations. And what are the unknowns? The unknowns are exactly those parameters that are in boldface. V final of 1, V final of 2. And now I'm going to eliminate the vectorial notation because it's a one-dimensional problem, okay? Every time that you deal with a one-dimensional problem, you don't need to put the vector notation there. 2 unknowns, 2 equations, okay? Most of the time that you have 2 unknowns and 2 equations, you can solve those equations. You can solve the equation completely, okay? And now we can go for another simplification that I could have done before. And the simplification has to do with the mass. Mass here cancels. the math on the left side cancels the math on the right side in both equations, right? So let me simplify here in this step. Mass, mass, mass. Oh, not just the mass, but half as well in the second equation. Half m, half m. Here you go. And now what we're going to do, we are going to solve. Now we will eliminate one of the unknowns of the equation to solve for the other unknown. Okay? And how do we do that? How do we eliminate one of the unknowns? We here write that unknown in terms of the other unknown. Let's see, let's eliminate VF2, right? I want to find VF1 first. If I want to find VF1 first, so I have to eliminate VF2. I have to make VF, and by eliminating VF2, I mean I have to make VF2 equal to the other one. That's what I mean by eliminating. I'm going to pass VF1 to the other side. It becomes a negative. Okay, and we write VF2 in terms of VF1. That's what I mean by eliminating VF2. I'm going to put VF2 on the left side of the equation. Equal. Like that. And I'm going to substitute this VF2 right in here. Okay? This VF2 right in here. That's what I mean by eliminating the VF2. And we are going to get this equation only in terms of VF1. In terms of VF1 only, right? Let's go here. Copy and paste. I'm going to put parentheses. And don't forget to raise to the square. This square here is this square right in here. I'm not going to erase this equation because I'm going to need it later on. But I'm going to expand the second equation. Right from the bat, you can see that we are going to get a quadratic equation. And every quadratic equation has two solutions, right? 2v naught 1, v final 1, v final 1 squared. Now I don't need the square in the parentheses anymore. Okay. Next step, I just copy the previous equation. Isn't that nice to do those derivations like that? You know, back in my time, we didn't used to have Excel. We didn't used to have Word, and we had to do all the derivations by hand. If you made a mistake, yeah, and it was very common for us to make a mistake when we were deriving equations by hand, you know, it was a nightmare to pick up where the mistake was. But now we have not just Word, but we also have symbolic software. Symbolic software can do all those calculations automatically for you. Okay, so here go, which is end up being much quicker than what I'm doing right now. Here you go, I'm taking out those three terms from the parentheses, and I am going to copy and paste it again. VF1 square, VF1 is square, becomes 2 VF1 square, right? So we do not need that anymore. What else? V01 square cancel out with the other V01 square right in here, right? So I'm going to make them 0. Okay. What happened to the other? Let's see here. Interesting. Yeah, it didn't. Okay. Okay. And now we have this quadratic equation that I'm going to rewrite it in a different way, equal to 0. The unknowns are going to be on the left side. VF1 is still not. Notice that I'm not doing anything with this equation, right? But I'm still keeping it around because at the end, I'm going to need to find what VF2 is. I will find VF1 with this equation, and I will substitute this result right in here in this equation to find VF2. Okay? That's, I'm going to put VF1, to VF1 in evidence. VF1, okay. Here you go. VF1 minus V naught 1, right? The 2V naught, the 2VF1, here you go. I put in evidence the 2VF1, 2VF1. And now you must be careful. We usually make a mistake when we see an equation like that, but don't make this mistake, okay? Otherwise, because if you make this mistake, you're not gonna get the right result. In order for this equation to be equal to 0, there are going to be two possible conditions, two possible solutions, not two possible conditions, but two possible solutions, okay? Two solutions for the above equation. Then we're going to find out which one is the physical solution for the above equation. Either, VF1 is equal to 0. Final velocity of 1 is equal to 0, or VF1 is equal, VF1 minus V naught 1 is equal to 0. Okay? Which means, what does it mean? It means that V final 1 is equal to V naught 1. Two possible solutions. And let's see which one is the correct one. Okay, two possible mathematical solutions. Okay, let me emphasize that. Two possible mathematical solutions for the above equation. Either the final velocity is going to be 0, or the final velocity of 1 is going to be equal to its initial velocity. Let's analyze both of those two solutions and see which one is the correct one. I'm going to, okay, and let's not forget we're gonna repeat the first equation, right? We can do that with the software. Okay. Very easily you can do that. It's just a copy and paste process, right? Let's take a look at this one first. And that's where that first movie that I showed to you comes about. I'm gonna copy this one here and paste. Right in here. Okay. The second solution, right, is telling us that the final velocity of 1, that the first object doesn't change its velocity. Okay. Basically, it's telling us that the first object approaches the second object. Okay. Makes contact with the second object. And then what does it say? It says that the second object passed through the first object passed through the second object, just like a ghost. Because the final velocity of 1 must be equal to the initial velocity, to its initial velocity, right? That's what this mathematical solution is telling us. So now you have to ask yourself, is it possible to have something like that? Is it possible to have a physical solution like that, right? It's not possible, right? An object, a solid object, cannot go through another solid object. That's why you must discern between a mathematical solution and an actual physical solution. So be aware of this caveat, right? Be aware of this caveat. The other solution is exactly what I told you before. It's exactly the one that I told before, right? Final velocity of one is 0. And let me substitute right in here. Let me come up with when final velocity of 1 is 0, then the final velocity of 2 becomes the initial velocity of 1. And I'm going to do the same. Yeah, here you go. I did the same here. Yeah. Right? And it's exactly that first one, that first condition that I illustrated for you. The actual physical condition during a collision like that. First object approaches the second one. They interact. The force that 2 applies on 1 is slow it down or even bring it to a stop. And the second object takes off with the same velocity that the first object had initially. Okay? So we prove mathematically using, and this thing is observed in real life. This type of situation is observed in the pool table, right? What we usually call that in my time when I was an undergraduate student, we used to call the pool table a laboratory of collisions. You know, I'm going to go to the laboratory of collisions. And then all my buddies would come along and we would play pool. Okay, and that's one-dimensional collision. Okay, so and then you have every other possible situation, right? You can have a larger object undergoing totally elastic collision with a smaller object, M1 greater than M2. But now the result is going to be slightly different because we have a larger mass, right? It's going to be difficult to slow down this larger mass. And at the end, the second mass is going to take off with a velocity, a final velocity, and the larger mass is going to move with a slightly smaller velocity. You can derive that. Using the equation. And something similar happens to a smaller mass that's colliding with a larger mass that's at rest, right? So what's going to happen? You know, here you go. The smaller mass approaching the larger mass. We have the same force acting on both of them. But now, instead of having the first mass moving in the same direction as the second one, the first mass is going to just bounce out of the first one. The first mass is going to bounce out of the second one. Okay? It is as though it is as though you're colliding against a wall, right? And then you change direction in your velocity. That's and then you have other situations, okay? We have here's another situation. An object, different masses M1 and M2, initial velocity of 1, initial velocity of 2. Now the object number 2 does have a velocity. Collides, okay, and it slowed down the first one, right? Depending on the mass. Depending on the mass, the object can either bounce out, like we saw before, or propagates in the same direction, depending on the mass. And for those who arrived late, right, so let me write down here. I posted your grades in Canvas, right? And now you can follow your total grade as we move along the semester. we move along the semester. Okay, I posted your lab one grades in Canvas. And as I keep on correcting the lab reports, I'll keep on update your grade online. So you see your grade, you will see your grade in real time. Let's see what we have here. Okay, don't forget chapter 3, 4, 5, right? Okay, 3, 4, 5. We have for exam 2. For exam 3, material for exam 3 so far. Here. Labs 2 and 3. Should be chapter 7. Okay, here chapter 6. Here you go. Go 3, 2, 3. Section 1, 2, 3, right? 4. 5, 6, 6, 7, 8, 9. And here I have to restart at 1. Here you go. We did collisions in 1 dimension. And I'm gonna show you a case. What time is that? Okay. Of a 2-dimensional collision, okay? Let's see if I have here in my notes. Oh yeah. Let's start with an example of a 2D inelastic collision. And I'm going to repeat here 1-dimensional collision. For exam 3, material for exam 3 so far. Okay, 1-dimensional collision. Inelastic collision, explosions, totally elastic collisions, everything else in between. In between totally elastic and completely inelastic collision, right? That's partial elastic collision. That's what this everything else in between is. That's that everything else in between is. I didn't do any. Yeah, I did it. Explosions in a way is the process of solving the problem of explosions is similar to the process of solving a problem in partially elastic collision. You have to know the final mechanical energy, right? And the initial mechanical energy. And now those are just 1-dimensional problems, 1-dimensional collision problems. When we add a second dimension to the problem, its solution becomes even more mathematically challenging, even more mathematically challenging. When I mean mathematically challenging, I mean the number of equations that we are going to deal with. Okay, in the case of inelastic collision, we have one equation, right, to solve the problem completely. One equation to solve the problem completely. Here you go. Solve the problem completely. But now, when we start talking about explosions, now we are talking about two equations to solve the problem completely. You have to have that here. This the solution for this type of problem does not require that you use conservation of energy. It does not require you use the equation for the conservation of energy. Okay, but the other ones require. The other ones require. This require, and this require. You go. Completely. And now that we're going to do something even more difficult, we are going to consider a second dimension. When we consider a second dimension, we add another equation to the whole system of equations. Okay? And let me do an example on 2D inelastic collision. Undergo a two-dimensional inelastic collision, giving their mass and their initial velocity. Given their masses and their initial velocities, find their final velocity. Let's see if I have an illustration here. Oh yeah, here you go. I do have it. This is a two-dimensional collision. Two cars approaching an intersection. Mass 1, mass 2, right? V01, V02. They are about to collide, right? When they collide, we have those forces that you see right in here. This force is going to make this car accelerate in a given direction. It's going to change the direction of the car. The velocity is initially to the right. This force is going to change the velocity direction, right? The direction of the velocity of the car. Somewhere in the direction of southeast, right? Somewhere. And they're going to stick together because it's a 2D inelastic collision. The exact angle is going to depend on the masses and the initial velocity. Here you go. The wreckage of the car, right? Eventually they end up somewhere around here. Friction will slow them down until they come to a stop. So officers, police officers, when they're investigating a collision like that at an intersection, they have to know this type of physics to understand, to have an idea who was speeding and who was not speeding, for instance, right? Who was speeding and who was not speeding, and they can have this idea. Another illustration here. Here you go. Two masses in the case of the pool table, right? We can have a glancing collision as well. The previous example that I gave you, it was not a glancing collision, it was a head-on collision. In a glancing collision, here you go. One ball takes off in one direction, the other ball takes off in another direction. And there is a very nice solution, very intuitive one for this case. I'm going to do those two. One for totally inelastic and the other one for totally elastic collision. So just like before, here you go, solution. First one, this one that you see right in here. Two objects undergo a 2D inelastic collision. Given their mass and their initial velocities, find their final velocities. Okay. Now, this equation here are two scalar equations. There is no need to write down the conservation of the equation for the conservation of energy, the inelastic collision. Let's see, someone asked the question. I was talking with myself. Okay, so let me see. Okay, let's talk about that. Go, break it down, break the linear momentum into two equations along the x direction and the y direction. Okay. P01x plus P02x, PF1x, PF2x. And then we have the y components. So we can break it down. MV01x, right? MV02x, M2V02x, and so on. Those are the two unknowns. Let me see. Let's see. We have 1, 2, 3, 4 unknowns, right? Right now we have 4 unknowns. VF1x, VF2x, VF1y, VF2y. But then there is one important condition for the inelastic collision that I still didn't use. The important condition for inelastic collision that is another vectorial equation. The final velocity of 1 is going to be equal to the final velocity of 2, which ends up being 2 additional equations, right? And now we have 4 unknowns and 4 equations. 4 unknowns and 4 equations. And I'm going to spell them out. One below the other. See how complicated those things can get, right? Now we're talking about solving a system of 4 equations, right? But the system of 4 equations is simple because it's just a matter of substituting VF2 by VF1, okay? Just a matter of substituting VF2 by VF1. And the problem arises when we have conservation of energy. Okay, now I'm going to substitute VF2x. Okay, I'm going to put everything in terms of VF1, okay? Everything in terms of VF1. Make it simpler. Now I don't need those 2 equations, okay? I already know that VF2 is equal to VF1. I go the next step. The next step is to collect the right side of my equation. Let's see here. I'm going to do it. I'm going to do like that. I'm going to collect VF1. Oops. I'm going to collect VF1 here too. VF1. And then we find out, now we can have VF1x, VF1. Let me see. That's not, okay, I put should be VF1y here, right? VF1y here. Making a mistake, don't forget. I had to pick that up, right? So we solve that easily in a straightforward sense. Like that, and that's what we get. That's the solution. 2-dimensional case. That's the solution. That is a solution for a 2D inelastic collision. Now we're going to do another problem, which is a very nice, very intuitive one. Totally elastic collision in 2D. And I have illustrated that right in here. That's inelastic, and that's the elastic, right? Glancing collision. Glancing collision. Right? The takeoff. Two masses, two equal masses, totally allowed to be along the same height. Only kinetic energy is conserved. Don't need to worry about potential energy. You know the mass and their initial velocity, and their initial velocity is mass of one is equal to mass of two. Mass of one is equal to mass of two. Okay. Solution. You have to have conservation of linear momentum, conservation of kinetic energy. We break down the equation for conservation of linear momentum into two equations, components x and y. Okay. And spell out what is P01 and P02 and PF1 and PF2, right? Plus kinetic energy of 1 and 2. I still didn't use the case in which you have, in which the masses are the same. Once we apply this condition, the mass being the same, the equation simplifies. Okay, here you go. Those are the unknowns. VF1x, VF2x, VF1y, VF2y. Okay. Okay, applying the condition that M1 is equal to M2, which is equal to M. Okay. This equation becomes this set of equations becomes simpler. And even better, okay. Don't forget the half here went away, right? That's why we're getting something like that. And now I'm going to apply this condition as well. The three equations have that mass canceled out. let me put it here. Totally elastic collision D along the same height. Only kinetic energy is conserved. Don't need to worry about potential energy. You know the masses. Mass 1 is equal to mass 2. And let's put another condition too. Mass 1 is equal to mass 2. And mass 2 is initially at rest. So we're going to make it even simpler. Initially at rest. Okay. If mass 2 is initially at rest, this term disappears. This term disappears. This term disappears. And this mass cancels out. Okay. Let's not forget, right, that VF1 and VF2 square is equal to VF1 in the x direction squared but plus VF1 in the y direction. Okay. And we repeat the same for the other ones. See how complicated it becomes. But then, if you look very carefully at this solution that you see right now, you will be able to find a shortcut. You will be able to find a shortcut. Okay? And let me show you what the shortcut is. It's a very nice shortcut. The shortcut we obtain by analyzing what you have here and the initial vectorial equation. Okay? Let's go back to the vectorial equation. Here you go, this one. Okay. Very challenging, mathematically speaking. Okay? Mathematically speaking. But there is a shortcut. There is a shortcut. An intuitive one and a very intuitive one. Okay? We are going to use this equation. And we are going to use the initial vectorial equation. Because the initial velocity of the second mass is 0, right? We can eliminate this term, right? So here you go. And on the top of that, because those two masses are the same, and oops, we can write down that M V01, right? M oops VF2, VF1. M VF1. Okay. We're going to see the nice shortcut we're going to have. M is going to cancel out. Once we solve that, we can have our break. It is 10:40 right now. Yep, 10:40. Mass goes away. Mass goes away. Mass goes away. Now, notice what we have here. Vector V01 is equal to vector V final 1 plus vector V final 2. On the top of that, we also have that the square of V01 is equal to the square of V final 1 plus the square of V final 2. You see that? And the intuitive solution is you have to remember that what you see writing here looks like the Pythagorean theorem, right? Notice that what you see in the second equation is just the Pythagorean theorem. Pythagorean theorem in a different format. With different variables. Furthermore, what you see right in here is like a triangle, right? This side of the triangle is equal to this side of the triangle plus another side of the same triangle. Can you picture that? Right? So I'm going to show you right in here. If I'm going to, here is the vectorial equation that you saw before, right? The vectorial equation that you saw before is saying that V naught 1 is going to be V final 1. Let's put let's leave V final 2 here. V final 2 plus V final 1, right? Or V final 1 plus V final 2, it doesn't matter. The summation between vectors is commutative. Oh, what did I do? Right here. V final 2 plus V final 1. And I'm even going to place this guy right here so you can have a bet. Oh, that's terrible. Let's make it larger. What's the size? 36. Size 36. And I'm going to boldface it. Now I can eliminate. Oh, I didn't eliminate it. Let me eliminate it. V final 2 here. I'm going to put V final 1 here. And I'm going to put V naught 1. V naught 1 right here. Make it look nice. See my triangle here? Now the question is that you gotta make yourself, what's the angle that you see right here? Which angle is this one gonna be? Okay, that's the question you have to ask yourself. What you see right here is just this equation. And the angle that you see right here, that you have right here, is going to be dictated by this equation that you see right here. Okay? You have to remember the law of cosines. That's what you have to do. Okay? This side here is equal to this side square plus this side square minus 2 times this plus times this times the cosine between this of this angle, right? But this equation is telling us that the angle that you have right in here must be 90 degrees. That's why we do not have the term. Here you go. I'm going to write that down. 2 plus 2 cosine of theta, right? And we still have V final 1, V final 2, like that, right? But in order for this term to disappear, the angle here, this 0, these 2 must go away. This angle here must be equal to 90 degrees, right? Because that was the original equation. Huh. Let's see if I can get it right. Yeah. Wow. If cosine of theta is equal to 90 degrees, then this term here disappeared, right? Which was exactly the equation that we had before. So this triangle that you have right here, consequently, must be a right angle triangle. Must have a 90-degree angle there. So when those two balls collide, you know, V fine of 1 and V fine of 2 must make an angle of 90 degrees. And that's the nice intuitive solution that we get for this specific problem. Right? Here you go. Even though it doesn't appear, this thing is supposed to be at 90 degrees. Even though it doesn't appear to be, that's what this angle is all about. It's not in the, it's not, let's see if I can get it. Yeah, let me get that. Let's see. Doesn't look like, right? 90 degrees, but it's supposed to be 90 degrees. Just the drawing that is incorrect. Okay? 90 degrees and put it right here. The angle between VF1 and VF2 is 90 degrees. The above equation, the above set of equations states that the angle between VF1 and VF2, the angle between vectors is 90 degrees. Like that, okay? And that's where we're gonna stop in this chapter. We're done with chapter 7. Exam 3 is going to be in 2 weeks. Exam 3 will be in 2 weeks, right? And we can go take our break. Any questions before we go into the break? We have 2 more minutes to talk a little bit here. Break, let's see. 1 minute now. Between 10:50, I want to make the break between 10:50 and 11:05 a.m. 11:05 a.m. Okay? Okay, so I see you in 15 minutes. See you soon. Stop sharing. Okay, I'm back here. And today is going to be lab number 4. Yeah, lab number 4. Okay. And okay. Insert page break. Let's see, someone's trying to get in. Hmm, not the one. Let's be this one here. Okay, so the next one is going to be projectile. Projectile motion. Okay, so okay, lab 4, projectile motion. We do this experiment in the lab, and here what we're going to do. I'm going to walk you through step by step how we perform the experiment in the classroom. But first, let me upload the spreadsheet for the lab. And let's make sure that those. Okay, that's good. That's good. Make sure everything is fine here. That's one of the few labs that we do not have a graph, okay? A graph to plot. I believe that's the only one that we do not have a graph to plot. It's just a statistical analysis of the results that you end up doing. Okay, and let me. Yeah, yeah, yeah. Okay, so let's go there to Google Drive. Fall folder. Okay, group 1, group 2, group 3, group 4, group 5, 6, group 7, group 8, group 9, group 10, 11, 12, 13, 14, 15. Okay, so everybody should have their spreadsheet there. Okay, and go ahead, download your lab report. I'm going to open one of those lab reports and follow it accordingly. Hmm. This one here. Let's see, this one here. Okay, that's the spreadsheet that you should see, okay? A total of 1, 2, 3, 4, 5, 6 tables. Total of 6 tables. And how this experiment is performed, right? Let me close this guy here. I will start with a table. And we have a table there in our classrooms. So we start with the list of equipment that's being used in this lab. Here we go, table. And then we also have a spring-loaded gun. Okay. So is the next one right in here. This spring is mounted over a support. Okay, we call that a projectile launcher. And we place it with its support over the table. Okay, so what we have here inside is a spring that we can load and launch a projectile. To make sure that the launcher is leveled using a bubble level. Bubble level, can put it here. And we are going to use a metal ball as a projectile. And we put this metal ball on the tip of the launcher. The tip of the launcher is just like a metal cylinder. Okay, and that you can fit the ball on it. The ball has a hole. Okay, the tip has this cylinder has a little tip here. Okay, and we can load the launcher. Note, see that right in here, the launcher is not loaded. So the spring is not compressed. That the spring which is inside here is not compressed. Okay, then we compress the spring, and this device has a trigger. It has a trigger, okay, that we can use to launch the projectile. What else do we need for this experiment? Let's see here. Bubble level. I gotta put the metal ball here. Metal ball as a projectile. Place it at the tip of the launcher, but do not load it yet. Load it. I tell my students when they're doing the experiment, do not load it yet, because if it fires accidentally, it can hit someone. Okay. Do not load the launcher yet. Okay. And what else we are going to need? We're going to need the photogate as well. We used the photogate before in a previous experiment. And that photogate, as you remember, has a resolution of a tenth of a millisecond. And here is the resolution written down, 10 to minus 4 seconds, right? 1, 2, 3, 4, right? That's 10 to minus 4. 10 to minus 4 seconds. 10 to minus 4 seconds. You need that to display the proper significant figures. You're going to use a ruler, a meter stick. Both the ruler and the meter stick have the same resolution. A masking tape. I'm going to tell you exactly what you're going to need for what you need the masking tape for. A plumb bob. I do not know if you're familiar with plumb bobs. We use plumb bobs in the lab as well. White paper. The white paper is used to mark, to document the point where the projectile landed, okay? And the carbon paper is placed on the top of the white paper to mark the position in black, right? Where the projectile landed. That's how it goes, okay? Experimental procedure. Let's go for the experimental procedure. Let's go. Loaded. Here's the launcher that's loaded, right? But leave the launcher loaded and put the ball aside. And then here you go. Here's the position of the photogate. The photogate is going to be used to find out the speed of the projectile. Okay, and it's going to be one photogate and a photogate accessory. Okay, what are you going to do? We're going to launch the projectile. The projectile is going to pass between those two photogates, and the photogate is going to measure how long it takes for the projectile to cover this distance. Okay? The distance divided by the amount of time is going to be the initial velocity of our projectile. Photogates. Okay, so you have to measure the distance d between the center of the two photogates to do this experiment. And that's where we start looking at the spreadsheet here. Okay, that's the distance d. Don't forget to display it with the proper significant digits. Gotta put that in meter. We're going to talk about y very soon. This guy here, very soon, we're going to talk about it. And what's next? Anchor the photogate on the table with masking tape. I tell my students to do that so you do not knock them out of place. The distance remains the same. Set the main photogate to pulse, which is a characteristic of the photogate. When you set the photogate to pulse, you measure the time it takes for the projectile to cross this photo gate and the other one. You know, the ball, once we fire the ball is going to pass through this photo gate first. The moment the ball passes through this photo gate, the timer is going to start. Once the ball passes the second photo gate, the timer is going to stop. Okay, that's how we measure the time it took for the ball to go through the photo gate. Okay, load the launcher. And when we propel the photo gate, when we propel the projectile is going to undergo a parabolic profile, right? A parabolic arc. It's going to describe a parabolic arc. But how? Let's go to the other one here. Put the photo gate aside, put the projectile aside, place the photo gate in front of the launcher. Okay. Place the photo gate accessory. The distance that we usually use between the photo gate is 10 centimeters. Okay. Measure the distance D with a ruler. So the distance D that you saw here in the spreadsheet is going to be around 10 centimeters. The resolution of the ruler is 1 millimeter, 0.001. Consequently, D will have to be written in terms of X. Let's see, since it's 10 centimeters, right? We're going to have two X's in front of the decimal place. 1, 2, 3. Measure with a ruler. Since we're measuring with the ruler, this guy should go right in here. Fix photo gate is a masking tape. Set photo gate to pulse, just like I showed to you there in the photo gate has 3 modes of operation, okay? Gate, pulse, and pendulum. In this experiment, we are going to use the second settings of the photo gate. Place projectile at the tip of the launcher. Fire the spring-loaded gun. That's the most dangerous experiment that we can do in the lab. You can hit by the projectile. Okay. When you fire the projectile is going to fly between the two gates, right? And the photo gate will measure the time of flight that it took to fly through the two gates. So the time t is going to be x.xxxx seconds. 4 decimal places in seconds. And now we can go right in here to this table. I'm going to get back to y. Don't worry about the y yet. The g is just have your value there already set up, right? Written down, 9.8 meters per second squared. And here, this is the table that we are going to use to determine how long it takes for the projectile to fly between the two gates. In this case, there are 10 consecutive measurements that we take. Okay, measurement 1 in this case is 0.0166, 0.0160, 0.0182, and so on, okay? There will be small variations because we're doing an experiment. In an experiment, there is slight variations from each measurement, even though those measurements are the same. Okay, and then what we're going to do, we're going to sum all those values that we obtained, and that's the summation, and we take the average. Don't forget, when you sum, you're going to gain, you may gain a significant figure here, right? You may gain a significant figure. This average goes exactly right here in the third table. Average, see that? Average of all the 10 measurements. So we fired the photo gate 10 times with the projectile. Let's see, fire the spring-loaded gun 10 times. Okay. flies between the photogate and the photogate measure its time of flight. Its time of flight 10 times. 10 times with a resolution of 0.0001 seconds. Here is each measurement that you have. Okay, x dot x, 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 x. And after firing the projectile 10 times, right? Calculate the speed of the projectile, the average. After firing the projectile 10 times, comma, take the 10 measurements and calculate the average time it takes for the projectile to fly between the two photogates. That's what it is that we do. So what else? From the above result, calculate the speed of the projectile. And the speed is this one right in here. You can see that it's going to be the distance d, approximately 10 centimeters, divided by the average time that the photogate takes to fly, okay? Then what do we do next? You calculate the range of the projectile for this specific situation. The theory, you should remember what the theory is from the previous lectures, right? So the range, let's see here, that the projectile is going to be given by the initial velocity of the projectile that you calculated right in here, that's the initial velocity, times the time of flight. This time of flight is different from that other time, okay? This time of flight here is different from this here. Here is the distance that the projectile cover between the two photogates. This t here is the time it takes for the projectile to reach the ground, okay? And this t is given by 2y0 over g square root, okay? D over t. See, I put the time of flight between the photogates at capital T, right? As capital T. I'm even going to emphasize that there is a difference, important difference between this big T and this small t. Y0 is our next measurement. Y0 is going to be our next measurement, okay? Here you go. You measure the height from the bottom of the projectile to the floor. That's going to be your Y0, and Y0 is right in here. Measurement, measurement. Let me highlight that, everything that's measurement. Here is also measurement. Actual measurement. Everything else is going to be calculations or results. Next. Okay. And how did I get this relation, right? Just go back to the equation of motion of your projectile. The equation of motion of your projectile is uniformly accelerated motion. Here you go. Uniformly accelerated motion, right? Y0 is equal to half gt squared, okay? That's how I got the square root of 2y0 over g. If I invert this equation, I get exactly what you see in there. Square root of 2y0 over g. Okay, after measuring the time that the photogate, let's see, I just list continue numbering. It's supposed to be n in there. Yeah, good. Supposed to be n, good. After measuring the time of flight of the projectile between the two photogates, right? Between the two photogates. And that I call capital T. We don't need the photogates anymore. Just remove the photogates and its accessory. Okay, and now what you're going to do next, you're going to mark the origin of the x-axis on the floor with a plumb bob. That's what the plumb bob is all about. Here you go. We use a plumb bob. The origin of my projectile is right in here. Let's see if I have the next one. I remove the photogate. Next is going to be the plumb bob. Okay. So I pass the plumb bob next to the center of the projectile, and where the tip of the plumb bob marks the floor is the origin of your x-axis. Let me show you a plumb bob. I have one here in case you have never seen one. Here's my plumb bob. Okay, it's a very simple thing. It's a very simple device. Some plumb bobs have a tip, just like the one you see in the illustration. This one doesn't have a tip. I prefer the one with the tip. Okay. It's a very simple device. It's just a string that passes through the center of mass of a heavy object. Okay. Professionals use that in the construction sites to get the vertical of the place. Okay, and we use that in the lab as well. Mark this position with a tape in the floor, on the floor. This is the origin of your x-axis. Why we are doing that? We are doing that because we are going to measure the distance, the range of the projectile from the spot wherever it falls. So here you go. Tape a white paper to the floor at the approximate position where the projectile lands. Okay, to the white paper that you saw before, and put the carbon paper on the top of the white paper. Do not tape the carbon paper to the floor, just the white paper. We like to reuse the carbon paper. Here you go. Here's our projectile, right? And we are going to measure this distance right in here. The launcher releases the projectile at this very position, which is the position where the tip of this launcher ends up when the pressure on the spring is released. That's the range. That's another important measurement that we're going to do. And the measurement on the range of the project is right in here. A total of 20. We do a total of 20 ranges. Let me highlight with yellow to remind you that this is a measurement. Here's a result. Is that equation that I displayed for you, right? Velocity times time of flight. Time of flight to reach the floor. Let's emphasize here in the notes. Notes, okay, I'm gonna write that down right in here. Note that there are two different times. T, which is a measurement of the time the projectile takes to fly between the two photogates. This time is used to find the initial velocity of the projectile, right? Projectile. And lowercase t, which is the flight time, which is how long the projectile takes to impact the floor. Okay, after being released, right? After being launched, better. Two different instant of time. The second one is not a measurement. Here you go. 1. We start. Big T, which is a measurement of the time projectile that to fly between the two photo gates. This measurement, let's put, is used to find the initial velocity of the projectile. 2, lowercase t, which is how long the projectile takes to impact the floor after being launched. This is small t, right? It's not a measurement, but a result. Okay? And let's see here if I can continue numbering, set number value. I'm gonna put that should be n, right? Let's see if it's going to, yeah. Maybe, you know what? Maybe, yeah, let's leave it this way. Mark the origin, fire the projectile and estimate its impact position. Tape a white paper on the floor at the approximation position of the impact of the projectile. Lay the carbon paper on the top, the carbon paper on the top of the white paper. Do not tape this carbon paper. Fire the projectile 20 times and measure the distance of impact on the floor with a meter stick X prime R. Okay. Okay. What else do you have here? Here are my 20 measurements of the range with the meter stick. And you're going to take the average value. This is the summation, right? Don't forget to use the proper significant figures here. Everything that's in red does not require significant figures. Let me put everything here in red. So you know here there is no need for a significant figure either. And we're going to analyze this data. Procedure for data analysis. No graph that you're gonna plot, right? So this is gonna be a simpler experiment. Let's see here, this guy. Let's see what I'm gonna do here. I'm gonna do like that. Yeah, here you go. Notice there are 2 different times. I'm gonna format this way. Make it easier to understand, right? To become better organized. Good. Now we have it organized the way I want. Procedure for data analysis. We are going to start with set numbering value A. Oh man, let's try it again. Huh. Why it's not changing? Oh. Let's try it again. For some reason, it is not setting numbering value. Good. Huh, it's not changing. It's supposed to display A, B, C here, okay? For some reason, it's not doing that. Calculate the average range. Calculate the average range, like I said, is right in here. Calculate the average range. Calculate the standard deviation sigma of the average range. What's the equation for the standard deviation of the sigma of the average range? Okay, it's given by, very important that you memorize that, is the value xi minus the average raised to the square and the summation of those squares divided by n square root. Okay. In our case, it's 20 measurements, so n is going to be equal to 20, I from 1 to 20. Okay, calculate the percentage difference between the average of the measured ranges and the predicted value. And what are you doing here? Here is the predicted value. Here's the predicted value. Here is the average of the measurements. Average of the measurements. So what we do, what we have right in here is the percentage difference between the average of the measurements and the predicted value. That's the percentage difference, delta. Don't forget to put the units, right? The proper, here is the standard deviation. Standard deviation, we do have this function in Excel, standard deviation of this set of values. And what else do we do? Okay, we're going to have our break very soon. Calculate the percentage difference. And then you have to calculate as well the values of the average range plus and minus sigma, plus and minus the standard deviation, and the average range plus and minus 2 sigma. That's what we have in this other table. See, plus and minus, plus and minus, plus and minus. Okay. And there is a statistical interpretation for those values. There is a statistical interpretation for those values. What do we find? We find that, here you go, in this specific case, the average value minus sigma is 2.40. And the other one, the other limit is 2.49. So what we find is that the number of measurements between those two values should be approximately 67%. Okay? So you're going to identify where those two values fall within this list of measurements. Okay? That's what you're going to do. You're going to sort them out from smaller to larger, fit where x plus and minus sigma is within this value, and those numbers that fall within x plus and minus sigma should be around 67%. This is a statistical result that we get. And in this case, because it's a larger range, plus and minus 2 sigma, you should have like 95% of your measurements should fit between those two values, okay? We are going to do that. How are you going to do that? You're going to sort those values here, okay? And let me document here. Sort. See where you are. Calculate the percentage difference. Yeah. Sort your measured ranges for smaller to larger values. You can do that in Excel. Okay. You highlight those values. You go to data, and then we have this function here, sort. Okay. Have this function. And then you go ahead and sort it. And now you have specify. Let's see what's going on here. Why it's not doing that? It's not letting me sort. Let me figure out why it's not letting me sort. Sort. Expand. Continue with the current selection. Okay, I have to click continue. So once you are sorting just one column, you have to tell Excel that you should continue with the current selection. Because why does Excel do that? Excel expects you to select more than one column, okay? But in certain cases, like ours one, you want to sort it out just one column, okay? The smallest to larger, and he sorted it. We don't see that being sorted because the numbers here are in exponential notation. It is right now is 11:50. Let's see. Let's finish, right? Count. You know, I'm going just to document what I said before. Here you go. Count how many measured values you have between X range average plus and minus sigma and X range average plus and minus 2 sigma. No graphs. And log there in the table. There are no graphs for this experiment. Come on, man. Yeah. Log the units, display the proper number of significant figures, sort the range values from lower to higher values, determine how many values of X are prime fall between this range. Okay, and it is 11:50 right now. Let's take our break. Break 11:50 a.m. to 12:05 p.m. Okay, and I see you in 15 minutes. See you. Bye-bye. We are back here. And let's share this screen. It is 12:05 right now. We'll be here until 12:50. Okay, so let's follow here. The first thing that you want to do is first thing, sort the ranges of the projectile from smaller to from shorter to longer range, right? So I'm gonna do that for you again. But I suggest that before you do the sorting, put those values here in numeric format, right? Here you go. So let me correct that first. You know, highlight the values for the range, and sort them, and format them in numeric format with the proper number of decimal places, right? So let's do that. Let's do that this time. Let's do differently. Because when we see something like that, we do not know which one is shorter, which one is smaller, which number is larger, right? So let's format cell number. I'm going to put with the proper number of significant figures, 1, 2, 3, 3 decimal places, right? 3 decimal places, and we get the right number of significant figures. And the value, and then I'm going to sort. I believe that they already sorted out. This one was already sorted apparently, but let's do that. Sort. Let's see. Here you go. First, highlight them, right? Go to data, click data, and then we have this option of sorting. It's a function in Excel. Click, and then Excel is going to complain because in general, he expects you to highlight 2 columns. But in our case, we don't want to sort in terms of 2 columns, right? We want to sort just 1 column. So you just click here, continue with the current selection, and then you sort. You're going to come another screen here, and you have the option to sort from smallest to largest or from largest to smaller, right? You want the smallest to largest. And then now my numbers are sorted. My measurements are sorted. You can see 2435, 39, 40, 47, 490 is sorted. 6265, 65, 73, 76, blah, 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 right? So it's sorted. And you want to format this value as well. Okay, let's format that. So we can see the number, what this number is, right? And we're going to place it with 3 decimal places, just like the other. Okay? And I'm going to do something else too. Here you go. I am going to, let's see here. I'm going to, there's a name for it, align to the right. So all the numbers here are lined up with this number right in here. See the 3 decimal places? So those are all measurements that we get with the experiment. The projectile flies 2 meters distance. The range is going to be 2 meters, 2.5 meters. Since we're taking the average of this value, before taking the average, we have to take the summation, right? And notice that because we sum like a total of 20 measurements, we end up with a number that has 5 significant figures instead of only 4. That's what happens when we sum several measurements. And that's what happens when we take the average of several measurements. We may increase, it doesn't happen all the time, okay? But we may increase the number of significant digits. In this specific case, the original measurement had 4 significant digits. Now, since I'm sum several measurements, we end up with 5 significant digits. And this number that you see right here, which is the average, right, of all those measurements, must have 5 significant digits as well, okay? So, what else we have to do, right? Here you go. First thing, highlight the values for the range and format them in numeric format and change their format to numeric format. Using the proper number of decimal places. You know, do the following. Here you go. Do the following. 1. Now, here you go. Highlight. 2. Sort the ranges of the projectile from shorter to longer range. 3. Values x prime plus and minus sigma, right? Calculate calculate the values and see where they fit in the table of ranges, right? So let's go here. So here you go. My x minus sigma is 2.450. That the lower value, it's 2.450 is right in here, right? 2.450, and then we write that down so you don't forget about it. That's the lower value. This guy is going to be larger than this one, right? And what about plus sigma? Plus sigma is 2.521. No, 2.450. 2.450. In my case, 2.450. Wait a minute. Oh, yeah, 2.450 is minus sigma. Plus sigma is going to be 2.497. This one right here. 2.497. 2.497 is right in here. 2.497. And then you go ahead, count how many values are between those two, plus and minus sigma, right? Between the plus and minus sigma. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We got 13 values. And we go here in this table, see, and number of values between x average plus and minus sigma, we get 13. In my case, it's 13. Maybe yours is going to be different, right? And I'm going to change the format to numeric format like that. And I'm going also to highlight as being red because we do not need to worry about significant figures in this case. And then you repeat for plus and minus 2 sigma. Plus and minus 2 sigma, we start with minus 2 sigma. 2.426, 2.426. 2.426 is outside this range. I'm going to put it here, 2.426, right? And again, I got to put it in the proper format. Format cell number 3. Here you go. 2.426. And what about plus 2 sigma? 2.521. 2.521. Oh, it's outside. Huh? 2.521 is right in here. So the number of values, measured values within the range of 2 sigma is all the 20s. 20 is 100%. So we put like it, 20. So 100% of the numbers fall within plus and minus 2 sigma. Theoretically, this number was supposed to be 95%. But because we use a very small number of measurements, only 20, we are getting 100%, okay? Here too should be around 67%. And I'm getting 65%. Not bad, right? That's all you have to do. And, right? And everything else that you know, you keep on doing, you do, right? So log the units, display the proper number of significant figures, right? So let's see how you're all doing. I'm gonna call you one by one. Lab today is the 19th. Right in here. Instead cut sound. So I want to know, Arturo Lagunas, are you there? Arturo Lagunas. I don't see Arturo Lagunas there. Next. Number. Next is Eric. Eric Alcala. Eric
Here.
Alcala. Okay. Did you have any problems there? Did you download your spreadsheet, Eric?
Yeah, I downloaded it.
Okay. Did you already sort the numbers?
Yeah.
Okay. Do you have any problems so far?
No, everything's good.
Okay. So first is formatting, right? Let's do the formatting first. And then you sort it. Sort. Edith Alexandrian.
Yes, Professor. I downloaded it, but I haven't gotten a chance to sort it yet.
Okay, you did download, but did you format at least?
No, I'm not able to right now.
Okay, so let's see. Eric, you did format it, right? And Edith is working on that. Working. So you did sorted, right, Eric? That's what you told me.
Yeah, I did both.
Okay, good. So you gotta fill up the tables right now. Next is Jawadia. I don't see Jawadia here. Next is gonna be Arwa. I can see, let's see here. Chat, are you there, Arwa?
Can you hear me?
Yeah, I can hear you. Uh-huh.
Oh, sorry. I think there was something wrong with my mic. Yeah,
Okay.
I downloaded it.
Okay, did you format as well?
No,
Yeah, what about sort? Did you sort the values as well?
not yet.
Okay, you're working on that. That's good. Catherine Perez. I don't see Catherine here. Ben Bengoy. Let's see, Ben seems to be here. Hello, Ben, are you there? I can't hear from, I'm not hearing from Ben.
Professor, he
Yeah.
messaged in the chat.
Oh, he messaged in the chat. Let's see. Okay, now I have it. Let's see. How do I access the chat? Oh, I see. People. Oh, yeah. Already formatted and sorted. Okay, that's good. Downloaded, formatted, and sort. What are you getting for n plus and minus sigma, Ben? N. How many data points are you getting for between plus and minus sigma? Did you count that already? For some reason, my values are in between. Between what? In between adjacent values. That's what you mean? Okay, yeah, just like I got, right? So here you go. See this one here. No, it's not this one. What the heck? That's strange. Oh, now I am confused here. What happened? Oh, this one. Okay. So see that? This value here is between those two, right? It must be the same thing that you're getting, right? Isn't that right? Yeah. Okay, so what do? You count this value here. You start counting from this value, the values that are between this and this other one. In my case, I got 13. I gotta see what do you get for n in your case, right? It's okay to be, within, right? So you have to start counting from the next one. So next here, Melissa, are you there? Melissa is not here. Delisha? Delisha?
Yeah, I'm here, Professor.
Okay, good. So did you download the spreadsheet, Delisha?
Yes, I already downloaded it.
Okay, formatted this as well?
I'm
Then-
still working on the sorting and formatting.
Okay. So we're gonna put it here working. Good. Next is Isabel Medina. I don't see Isabel here. Queen Castaneda.
Hello.
Hello. Did you download the spreadsheet?
Yes.
Okay. Did you format it as well?
Yes.
Okay. Did you sort?
Yes.
Okay. How many values did you get between the
I
plus
have
and
not
minus?
counted yet.
You didn't count it yet? Okay, so I'm gonna put that you're working on that. Okay. Next is Emily Serna.
I'm here.
Okay, thank you, Emily. Did you download your spreadsheet?
Yeah, I downloaded it. I'm just still working on the sorting and formatting it.
Okay, working. Okay, good. So let's go for Gabriela now. It's Gabriela here. Okay, good. Did you download your spreadsheet, Gabriela? Okay, did you formatted it as well? Working on that now, okay. So let's go for Carlo Gallardo. Gallardo is here, right? Is Carlo there? Oh,
Yes, I'm here.
okay, good. Okay, did you download your spreadsheet, Carlo?
Yes.
Okay, did you format it?
No, not yet.
Okay, so you're working on that. Okay, Angelica Franco.
I'm here.
Okay, Angelica, did you download your spreadsheet?
Yes.
Okay, did you format it?
Mhm.
Yes, okay. Did you sort it out as well?
Yes.
Okay, how did you count how many numbers do you have between plus and minus sigma?
I got 10.
Not yet?
I got 10.
Oh, you got 10. Okay, you got 10. 10, that's 50%. Okay, that's okay. Now do for plus and minus sigma. Do you do for plus and minus sigma as well?
No, not yet.
Okay, so you're gonna work on that.
Can you explain how to do that one again?
What did you say?
Can you show how to do that one again?
What, the plus and minus 2 sigma? Yeah, it's you're talking about the plus and minus 2 sigma, right?
Yes.
Okay, so here you go. The numbers are already here for you, right? See, it already calculate your sigma, which is your standard deviation, and the spreadsheet already calculate everything for you. In my case, the x average minus 2 sigmas was 2.426. It's already calculated. Don't forget that there must be units here, right? 2.46, we have to look at those numbers. You can see that 2.46 is smaller. In my case, falls before this value, right? Before the smallest value. And the other one, plus 2 sigma, is 2.521. 2.521 is greater than the largest value. So plus or minus 2 sigma, you have 20 of those measurements between the values plus and minus 2 sigma. And then what did I write down? I wrote down and here equal to 20. In my case, it's 100%. The correct number should be 95%. But because I have only 20 measurements, okay, I didn't get 95%. You usually get 95% when you have like 100 measurements or more.
Yeah, I got 20 for mine.
Okay,
For
that's
the
good. Yeah, okay, that's good. So now you can do the rest, right? Don't forget the units, right? Gotta display the significant figures and so on. Let's get the next student here, Princess.
Hello,
Okay, hi. Did you download the spreadsheet, Princess?
I did.
Okay, did you format it?
I did format and sort it already.
Uh-huh. How many are you getting for plus and minus sigma? How many values are you getting between plus and minus sigma?
I counted 9, but I don't know if that's right.
Okay, 9. 9 is what, 45%? That's okay. Yeah, that's okay. And what about 2 sigma? How many values did you get between 2 sigma?
I got 20.
You get 100%, right? Okay, that's good. And you can continue working on the rest of the spreadsheet, okay? Brandon Guerrero. Brandon here. Doesn't look like he's here. Janie Maldonado. I don't see Janie here. Next is Montserrat Morales. I don't see Montserrat Morales either. Nicolas Rivera. I don't see Nicolas. Jason Cervellon. Jason is here. Okay. Good morning, Jason. Good morning, not good afternoon, right?
Yes.
Did you download their spreadsheet?
Yes, I downloaded it.
Did you format the numbers as well?
I'm formatting it right now.
Okay, so you're working on that.
Yes.
So let's go for Armand right now.
I'm mute.
Okay, Armand, did you download their spreadsheet, Armand?
Yeah. Yeah.
Did you format the numbers as well?
I did.
Did you sort them?
Yeah.
What did you get for the number of
I got 12 and then I got 20.
12 and 20? Okay, 12, let's see, 12 is 60%. Okay.
Yeah.
Okay, good. So you can continue doing the other things. One,
Professor.
yeah.
So for mine, I miscounted. It's not 10 because I didn't count from the next one up. So I got 9.
Okay, Franco, right?
Yeah.
Okay, so it's 9. Okay. 9 is 9, 45%. It's 45% that you're getting there. What about the other one? Did you manage to do the other one for 2 plus and minus 2 sigma?
Yeah, I got 20.
You got 20? Okay. 100%. Good. Juan Torres Arellano. One is here. Okay, she working. Okay, but you download the spreadsheet, right? What about the format? Did you format the numbers? In that table? Okay, I'm gonna assume that you're working on that. Okay, good. Thank you. Cecilia Chavez.
Hello.
Hello. Did you download their spreadsheet, Cecilia?
Yes, I downloaded it.
Did you formatted it?
Yes.
Okay. Did you sort?
Yes.
How many values do we have between plus and minus sigma?
12.
Well, okay. And what about plus and minus 2 sigma?
I counted 19.
Oh, you count 19. Okay. 19 is 45. 45, no. It's 95%. Okay, that's good. So you can work on the other stuff that is here you go. Insert. So what you have to do, units, right? Gotta work on the units. Gotta work on the sig figs. Sig figs. Okay, next one is Jacob Contreras. I don't see Jacob Contreras here. Evelyn Ayala. I don't see Evelyn. Isabella Cisnero. I don't see Isabella. Trin Hernandez. Okay, Trin, are you there? I can't hear from you, Trin, so let's move to the next one. Elizabeth Saldana, are you there, Elizabeth? Elizabeth is not here.
Sorry, Professor.
Yeah.
I wasn't able to download it yet.
Uh-huh.
My Wi-Fi is down. So I'm just using my phone.
Okay, so you're working on that.
Yeah.
Okay. So what about Elizabeth? Elizabeth's not here, right? Next is going to be Kimberly. Kimberly Morales. Kimberly's here. Did you download your spreadsheet, Kimberly?
Yes.
Okay. Did you format the numbers in the table there?
Yes.
Okay. Did you sort them out?
Yes.
Okay. How many numbers do you get between plus and minus 2 sigma? Plus and minus sigma?
13.
13. Okay. 13 is 70%. No, it's 65%. Okay. Yeah, 60. That's good. What about plus and minus 2 sigma?
20.
20. Okay. 100%. And then you can work on the units and the sig figs. Okay. It's 12:33 right now. We have, 20 more minutes? Yeah, 17 more minutes. And we have 16, 17 students. Going back to Eric, right? Eric, did you manage to to count the numbers between plus and minus sigma?
Oh, not yet. I'm still working on it.
Okay, here you go. Plus sigma, plus and minus sigma. Here is going to be plus and minus 2 sigma. Plus and minus 2 sigma. Next is going to be Edith. Did you format the numbers, Edith? I can't hear from you, Edith. Let's go for Arwa. Did you sort the number, Arwa?
I'm still working on it.
Do you need any help with the sorting?
Not for now.
All right. Do you know how to do it?
I'm trying to figure it out.
Oh, okay. So then, just to refresh your memory, right? You highlight the numbers that you want. You click on the data right here, and then you have sort. Okay. If this window appears, you just continue with the current selection. That's how you do it. And next, Catherine Michelle is not here. Ben Doy, did you get the numbers between plus and minus sigma? Ben? I got 12 and 19. Okay, 12 and 19, that's good. Here, 12 is going to be 60%, 19 is going to be 95%. That's good. So work on the rest, units, significant figures, and so on. Delisha. Looks like Delisha left. Okay, I'm going to put it here left. Isabel is not here. Queen Castaneda. Okay. Did you count the numbers, Queen?
I believe it is 12, but I am gonna recount.
Okay. You think it's 12. What about the 2 sigma minus 2 sigma?
Still working on it.
Okay. So let's see. Emily Sedna. Emily left. Right. Next, Gabriela. Gabriela is not here either. She left. Okay, Carlo Gallardo. Oh,
Okay.
okay. Did you progress there, Carlo?
Yeah, I formatted it.
Okay, you formatted. What about the sorting? Did you do the sorting?
For the sort, do I click on custom sort?
Yeah.
Because I'm given that option.
Costume sort.
Or can you show me again how to sort
Yeah,
it?
here you go. So you highlight those numbers on the third table. Let's see. No, the fourth table, table 4-4. Okay. But highlight only those numbers, right? Then, then you go to the top here. You have all those, right? Options. You click on the data. And then you have sort right here in the middle of the screen, the top of the screen. Okay?
Oh yeah, because it's different on my end.
Huh?
It's different on my end.
Yeah. Are you using what? Macintosh?
I'm using Chromebook, but do
The Chrome has less options. That's a problem. I
yeah.
have never used the Chrome, so I do not know how it displays in your screen.
Mm-hmm.
Try to use the help feature of Excel. Maybe you can figure out how to do that. Sometimes, yeah, right click doesn't help. But do you have those options there in Chrome? Like a file, home, insert? Do you have all those?
Yeah, I have those options, but
You have.
no.
What about data? Do you have data there?
Yeah, I have data.
Okay. But you cannot find sort?
Well, it only shows sort ascending, sort descending, and
Oh,
custom sort.
that's what you want. You want sort ascending.
Oh, okay.
You want sort ascending. Because if I click here, see, my computer has this additional step. For some
Oh
reason,
yeah.
continue is the current selection. And then I have C smallest to large is ascending. Largest to smallest is descending. And then you have a costume list. Okay? So that's what you
Oh
use. Costume ascending.
yeah. Okay, I sorted it out.
Okay? That's Carlo, right? 5:40 and 5:40, 12:40. 10 more minutes to go. Let's see, Angelica. So are you working on the units, Angelica?
Yeah, I'm still working on it.
Okay, good. Units and sig figs, right? Princess, are you working on the units?
I am working on the units, but how do you know exactly the units for the table?
Okay, so let's see here. Let's go. You gotta know what D is, you gotta know what Y is, right?
Mm-hmm.
They're both lengths. D is the
Mm-hmm.
distance between the two photo gates.
Mm-hmm.
Y is the vertical distance of the projectile. Here you go. Let's see, let me show you Y here. Here you go. So because it's a distance, you already know what the unit for distance, right? So you write down the unit for distance. Okay.
Okay.
Here is the amount of time. So that's why we have seconds here from the start. In the next one, this guy here, if you click on the cell, you're going to see that you are taking the average, the average, right, of all those numbers. Because those numbers has a unit of seconds, so the unit here should be what?
Seconds.
Seconds as well, right? Then what about this one, V0? V0 is H7 divided by G32. H7 is D. Unit of D is meter. Divided by G32, the unit of G32 is seconds, right? So you put the unit here for V0. XR range, right? Is that equation that I wrote down in the notes here. Let's see, where's the X range here? Where is the equation? I wrote it down. disappeared. Wow, I do not know how it disappeared. I typed this equation here, didn't I? Well, anyway, range, what's the unit of range? The unit of range is the distance, right? So you put the unit for the distance there. Yeah, for some reason, I erased it. Huh, interesting. Let me copy and paste it here. Calculate the range of the projectile. JKL. Yeah, just supposed to be here. Calculate the range of the projectile, and I'm gonna copy and paste it here. Whoa. Here you go. Okay. X range is velocity times time, right? And what else? X range. Okay. X range is a measurement. Here's a measurement. Here's a calculation. Here's a measurement. They should have the same units. And, oh, okay. X range average, right? And here for sigma, you have to look at the equation and do dimensional analysis. Okay, and I display it, the equation for the sigma. The equation for the sigma is right in here. Okay, do your dimensional analysis here, right? This guy has meter, this guy has meter too. You square them, become meter square. You sum, when you sum, you still get meter square, and then you divide by a natural number. A natural number doesn't have a unit. So you have meter square inside the square root, right? The square root of meter squared is equal to, right? Then you put the unit there. Delta is the percentage difference, so you put in there. Here is a unit of the range average. Okay, here's the unit of the range average, and so on. Now, what else? So those are the units that you have to worry about. Okay. And then you have to worry about significant figures, right? There you go, significant figures here, significant figures here, significant figures here, significant figures here, for all of them, including and significant figures here. You don't have to worry about significant figures of the ones that are in red. Okay. Now where we are Princess, right? Brandon is not here. 4 more minutes to go. Jenny, that's not here. Armand, do you need any help, Armand?
No, I finished.
Oh, you're finished. Okay. So unit sig fix. Okay, so if you want to go, you can go. Before you go, right, let me just write that down here. This spreadsheet. This lab report is due 11/26. Yeah, 7 days from now. 25. Yeah. Lab report. Report for lab 4. Okay, go. Report for lab 4 is due November 26. 3 more minutes to go. Okay, I was in so Cecilia, do you need any help, Cecilia?
Maybe?
Okay.
I did my significant, is it just 4 significant figures that we're doing? For table 4.2?
4.2. Okay, 4.2. Here you go. Depending on the value, right? So let's see. I'm going to put in format here, numeric format. Remember that I told you how many decimal places do I have to have for the measurement with the photo gate?
3.
No, decimal places, right? Three decimal places?
Yes.
No, it's not 3 decimal places.
No? Oh, let me check.
Yeah, decimal places for the photo gate is. Take a look here at my screen.
Oh, okay. So 4.
4, yeah, 4 decimal places. So let's display it at 4 decimal places. 1, 2, 3, 4. Okay. So how many significant figures do I have now? Can you answer me that?
Is it 5?
No, it's not 5.
Or sorry, 3?
D3, yeah. Zeros to the left of the leftmost significant digit is not, right? Is not a significant digit, all right? So yeah, it's 3 significant digits. Okay. And let's see, everything here should be 4 decimal places.
Okay.
4, that 2, 3, 4. Let's see how it looks like. Yeah. And then
3,
this guy is a sum. And now look, here we have 3, right? Here we have 3 significant digits, blah, 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 blah. But how many significant digits do I have here?
The 4.
Yeah, this one is 4. Okay, we gain a significant digit. We gain a significant digit. Sometimes we gain a significant digit when we sum several numbers. Okay?
Okay.
Okay, so let's stop here, right? 1 minute to finish. You can stop here. And if you do not have any questions, I'll see you Monday.
Thank you, Professor.
Welcome.
Professor, I do have a quick question. It's not regarding to this lab. I noticed that my lab, I think the lab 3 was a template and not actually the actual lab.
Let me see. Let me see what's the problem. You're talking about your. Wait a minute. Let me finish. Let me stop the recording first. Pause.